In this video, we're going to look at identifying the key elements that make up our conic section known as the hyperbola. So when you're looking at the definition for the hyperbola, the definition states that it's the locus or the set of points such that the difference of the distance from any point on the hyperbola to two fixed points remains constant. So just like in our ellipse, those two fixed points are going to be known as the focus points or the foci. And if we choose the distance from one of those focus points to a point on our hyperbola, and then go from that point to the other focus point, the two distances subtracted remains constant. So unlike the ellipse where the sum remains constant, here if you subtract those two values, it's always going to remain constant for all the points on the hyperbola. Now, as we go through the hyperbola vocabulary, we're going to see that there's a lot of similar vocabulary to our ellipse. I always kind of think of a hyperbola as an ellipse that was kind of blown outwards. So instead of opening up towards each other like this, they kind of get blown out away from each other. And the other thing that we want to point out is that each piece of the hyperbola that we're looking at is known as a branch. And so just like our ellipse had two different types of axes that we studied, whether it had a horizontal major axis or a vertical major axis, our hyperbolas can do the same thing. So our branches can open left and right, and we get a horizontal hyperbola, which is what we see in this diagram here. Or we get a vertical hyperbola when our branches open up and downward like this. And you'll see on both of those diagrams, I have a whole bunch of points labeled, and we're going to go ahead and identify all of those key characteristics and learn about the pieces that make up our hyperbola. So similar to our ellipse, we're going to call the center point HK. And in each of those diagrams, the center point is going to be represented by that dot right there, where the axes are kind of coming together here. So if the center point was the origin, then our point would be 0, 0, as is illustrated in this example. But if we shift it away from the origin, then the center HK would be this point anywhere on our coordinate plane. And it's always going to be at the midpoint of our two foci. So our foci are going to be inside the branches. So here you can see in this guy, when this branch is opening left and right, my foci are going to be those 2 points right there. So this is one focus. This is another focus. Or when my hyperbola opens up down, it's going to be these 2 points right here. So right in between the middle of those 2 points, if I find the average of the coordinates, I'm going to get my center point HK. Here on my 2 focus, I'm going to get my center point HK. So now when we look at it, the vertices are going to be the turning points. So in other words, that's kind of where my branches are starting to bend away. And so my vertices are going to be these 2 points, and they're going to lie on the same line as our focus points. So this here would be a vertex, and this would be a vertex. It's kind of like, they look like parabolas, and our vertex is that maximum and minimum point of our parabola. So it's kind of that same idea here. It's kind of that turning point for each of those branches. When it opens up down, this here would be a vertex, and that would be a vertex. So now, as you can look at it, you can see in each of those diagrams, I have this little like rectangular box drawn in. And as we create that box, that's going to help us create our shape if we were to graph these. So similar to how our vertices in an ellipse are A units away from our center, well, the same thing is happening in our hyperbola. Our vertices or our turning points are also A minus away from our center. And we're going to say they're plus and minus A units because they can be A units to the right and A units to the left, or they can be A units above and A units below, depending on our turning points. Now, the interesting thing is that our co-vertices are not actually on our ellipse they're not actually on our hyperbola. But we're still going to need to find them so that we can create this rectangular box. So our co-vertices are going to be these 2 points that are on this axis that's perpendicular to the line that contains our vertices and our foci. And our co-vertices are also going to be just like they were in our ellipse, b units away from the center. So they're going to move in the opposite direction or the perpendicular direction as our A coordinates. So if my A's move left and right, we're going to go B units up and down to create these co-vertices. I just wrote co-vertex. Or if my A units went up and down to my turning points on my hyperbola here and my axis was vertical, my co-vertices are going to go horizontal B units away to the right and B units to the left. So we would get a co-vertex here and a co-vertex over there. So our co-vertices are going to be plus or minus B units away from the center. So the good news is same vocabulary as our ellipse, same relationship. It's just they look different when we're working with a hyperbola. So now we're going to finally bring in some names for those lines that are creating the lines of symmetry for our hyperbola. So the transverse axis is, depending on your textbook, the transverse axis is sometimes known as this line that contains your focus points and your vertex points. So here it would be this horizontal line, or it could be this vertical line here that contains our vertices and our foci. So that line where the focus points and your vertex points lie on, that's known as our transverse axis. We're going to consider only the segment. So we're going to look from one vertex straight to the other vertex, and we're going to consider just that segment our transverse axis. And so if we're going from one vertex straight across to the other vertex, and each piece of that is A units, then I think it makes sense that our transverse axis would connect the vertices and have a length of 2A, whether it's going left and right or up and down like this guy right here. And that perpendicular line that's passing through the center, that's perpendicular to our conjugate axis, it's going to connect the co-vertices. So it's going to be perpendicular to our transverse axis. It's going to go right through our center. And we're going to look at just the distance from one co-vertex to the other. And so those distances, obviously up B and down B, would give me a total length of 2B. And it's that length of 2A and 2B that's really creating the rectangle here when we look at it. The final thing that we're going to talk about when we are looking at our branches is to kind of figure out how exactly, we know where the turning points are at our vertices, but if we want to know exactly how these branches are opening up and down or left and right, what we're going to create are two asymptotes. And we know that asymptotes are lines that as your x values increase towards positive or negative infinity, it's what your graph approaches that line. And so as I'm approaching this here, what I can see is I get these two intersecting lines that my branches want to approach. And they look kind of the same whether we're looking at one graph or the other. So the asymptotes are these diagonal lines that guide the curves. And we're going to be able to use our values for B and A to write the equations of those asymptotes. And we're going to look at that in a few minutes. And then finally, just like in our ellipse, our foci were C units away from our center. The same thing is going to happen when we are looking at our hyperbolas. So each focus point is going to go from the center C units away. And whether it's C units left or right, if my branches are opening left and right, or C units up and down, if my branches are opening up and down, my focus points are always going to be C units away from the center. And since it could be positive or negative to represent the up and down or left and right motion. Now, obviously, we can see our values are from A and B are coming directly from our vertices and our co-vertices. That value for C, similar to our ellipse, we have to build. So it's interesting in this case right here, but our formula to find C is actually the same as our Pythagorean theorem. So when we're working with a hyperbola, our formula to find C is just C squared equals A squared plus B squared. So those are all of our key characteristics. And what we're eventually going to be doing is looking at how we can use these key characteristics to write equations or take an equation that's given to us and draw a graph or identify these key points. So the last thing we're going to look at to wrap up this quick lesson right here are some equations that we're going to be using throughout our hyperbola unit here. So the standard form for our hyperbola looks like our standard form for an ellipse, with the major differences to kind of make the branches blow outward instead of inward towards each other is we're going to change it from a plus sign in between our two fractions to a minus sign. So we're still going to use HK as our center. So my numerator is still going to start out when I have a horizontal axis. As that quantity of x minus h squared. But now we're going to put a minus sign for our hyperbola, and then our numerator of our second fraction is going to be the quantity of y minus k squared. Like our ellipse, it's going to equal 1. But the main difference when we're looking at our hyperbolas is when it's a horizontal axis, we put the quantity of x minus h squared first, and then our denominators are a squared and b squared. But when we have a vertical transverse axis and my branches are opening up and down, what we're going to actually do is actually put the y quantity first when it opens up or down. So that's the biggest difference between a hyperbola and an ellipse. We know that in an ellipse, it always is x minus h quantity squared in the numerator of our first fraction, but in a hyperbola, that's not always the case. And the other main difference is now that we're also allowing that y to go first, our denominators stay a squared and b squared. Because when we're looking at our ellipse, our hyperbolas, when we're working with the horizontal transverse axis, we want to go a units away, left and right, to create that. And so that's why we're putting the a squared with the x. When we have a vertical transverse axis, we want to go up and down a units, and that's why we're still keeping the a squared in that first fraction, because we actually changed what that numerator is. The other thing that we're going to look at is our transverse axis is going to be always equal to whatever, when we're looking at our transverse axis, it's always going to be at the height, when it's horizontal, it's always going to be at the height of the y coordinate of my center. So if my center is at each k, then my transverse axis is going to be at that line y equals k. And my conjugate axis is always going to be at the value for h, because again, it's going to pass through that center. So my conjugate axis is always going to be x equals h. If we flip it around right here, my transverse axis is now going up and down. So it's going to be a vertical line. So it would be at x equals h. And my conjugate axis would be perpendicular to that. And that would be the horizontal line at y equals k. And then finally, the last thing we're going to end up using as we're identifying our characteristics is our asymptotes. And what's going to happen is if you know your point slope formula, our point slope formula looks like this. We're going to write our asymptotes in this idea of our point slope formula. And what we do is instead of using any point we want for x1, y1, we're always going to choose the center point. So this is always going to be h, and this is always going to be k. And the other thing that a lot of books likes to do when they're trying to rewrite them as we're creating these points they like to add that value over. So when they're replacing x1 and y1 with h and k, they also like to make it look like y equals format, and so they're going to add that y1 over, and again, y1 would just be k. So the only thing we have to do is figure out, well, what are the slopes for our asymptotes? And they have the relationship. We know slope is rise over run. So if we look at these diagonal lines, when it has a horizontal transverse axis and a vertical conjugate axis, my slopes are going up b units and then over a units, or they're going, that would create this diagonal line right here, up b over a, or they're going down b and over a units. So when we write our equations for our asymptotes in our hyperbola, the slope for this type would be positive b over a or negative b over a. So we're going to write positive or negative b over a to write both equations at the same time. And then that x minus h plus k. And when we had a vertical transverse axis and a horizontal conjugate axis, my diagonals here, or my asymptotes here, are now going up a units and over b units, or down a units and over b units. So my slope here would be negative and positive a over b, and then the rest of my equation would look the same. So those are all of our key characteristics. So when we go into the next part of our lesson, we're going to start looking at how we can use characteristics to write equations in standard form, or how we can take equations from standard form and identify our vertices, covertices, axes, asymptotes, foci, all of those things that we can look at.